round 3 of the Control Z experiment. So what have I figured out so far? So at an intuitive level, first point, I want to make clear one thing. It is not still clear for me what's the intuitive benefit of having different types of measurement, right? So everywhere, all over the place, they talk about like measuring on the z-axis, they're measuring. I get the mathematical correctness of it. I understand that when you go down one level, you see that, sure, depending on how you measure qubits, then you're gonna see things differently. But at an intuitive level, I think what my current intuition tells me, you you know you're probably gonna pick one measurement and then just get on with it. And so I think I'm gonna just stick to the z measurements always, and try to build the intuition from that perspective, because maybe that's an easier way to do first. And when my current understanding is when you have a state that it's like in a superposition. Let's say the control. Let's say the qubit 0 is always going to be controlled. So this is in a superposition, and then you apply whatever controlled operation. You're basically creating different types of entanglement, different types of correlation, right? So with the control X, you're creating a correlation where they always agree, right? No matter what, it's just they agree differently, 50% of the time, but they always agree. So that's useful. I guess that's useful. When you do a control Z, nevertheless, you have the situation where they agree and disagree 50% of the time. So that might seem useless, but they always agree and disagree in the same way. So maybe that has some utility. But from an intuitive perspective, that's what it creates another type of entanglement, so to say, of correlation. And just, it's probably out of scope for this, but control Y. So control Y, that's a funny one. Why is now red? Oh, I see that this went to the face. Woohoo! That's fun territory. Okay. So control Y gives you effectively also something where they always agree, but you've got a bit of extra information here, where you have like a negative complex component, and that's where all this extra information can be processed. That's interesting. And the reason why I think because you say, yeah, okay, they agree and disagree. When you do control Z, they agree and disagree 50% of the time. It's like, well, how is that then different from just having like a superposition? Well, it's different in the sense that here they also agree and disagree theoretically, or half of the time, but you're not controlling how they agree and how they disagree, and that might be relevant for whatever you're trying to solve. So, and I think this is what's mind-blowing about all this, is that it's not just it's not just the way that you're going to measure things at the end, but it's like in between, when you start solving a problem and your final measurement, you can play with a dimensionality that is just mind-blowing, because at the end of the day, you can make the same statement as I said here. Half of the time they agree, half of the time they disagree, in theory, right? But if we go and we do this, yeah, half of the time they agree and disagree, but in a sort of a different way. And that's pretty interesting. That's actually pretty interesting. So that's kind of summarizing. It's interesting. This and this and they agree, and then and versus if you take a look at the density matrix from that perspective, you see that it's just way noisier in terms of what's going on in there. So the control Z does this. That's cool. Now, what happens? So this is when the control bit is in the Hadamard state. Now we're gonna so it's a different type of correlation. Let's see what happens when we have both qubits in a superposition. So that's our starting point. When you do a control NOT, nothing happens. So in this case, the control knot doesn't have any effect. Density matrix is the same. Again, just to make sure that we're not experiencing some mistakes, simulator, let's go ahead. So this is here. We'll take a look at it in a second. If now though I use a Control Z, boom. Wow. Let's see again if that's also correct, but it seems like it just killed it. Okay, so this just destroyed the whole thing. It just destroyed the superposition. But let's see. Let's simulate that. So let's take a look at the one that we just submitted. So and see if that's the way we expect it to be. So we said we have a superposition, and then we apply a control knot, and basically, oh, you see, it's not that nothing happens. It's that it's always going to be 0, 0. Wow. Because if that's a 0 and that's a 0, stay 0. So if here's a 0 and then here's a 0 and then say 0, 0 and here's a 1, yeah, it's confusing, right? Because it can be 0, 1 and then you would still have 0, 1. Boo. It's tough to grasp. It's not intuitive. It's not. And anyway, it's difficult. So and here, so let's see if that really is what we think it is. It seems like, wow, really? Ooh. Interesting. That's definitely interesting. So, and what? And if you have a control Y, look at this. That's getting interesting. You see, that's cool. That is awesome. Really, this tool is pretty awesome. So that's basically flipping the sign. So you, yeah, it's interesting. That's interesting. It's like really that's honestly, that's kind of all I can figure out. I mean, so far, because one of the things that I'm going to do is I'm going to go and read the guides, the IBM Q Experience guide in the next videos, and then see what happens if I gain more understanding. But I mean, that's awesome. You see how this evolves, right? But you see, okay, so basically the Control Z is, so the Control Z, if in this configuration, it's doing that type of entanglement, which you can play with, of course, because if you have an X here, then you've got something different. It's just mind blowing. Can I do that? It doesn't have any effect. Of course, it doesn't have. Oh, good. So in this case, they agree and disagree, but also you have, the kind of minus in here. So they also kind of agree and disagree. It's just the space of possibilities is mind blowing. This is fucking mind blowing. It's mind blowing. Mind blowing. And what if I do this and this? Yeah, those things are just operations on the y-axis, I guess. Because why would I want to do that? We'll go back here, we'll go back here. So basically, what this is what's telling me. It's another type of correlation where they agree and disagree half the time, but they will always agree and disagree in the same way, and that is an interesting thing. I'm curious. I'm curious what would happen, and that's way too out of scope. But if we'll go to 3 qubits, and then we would do something like that. Boom. It's kind of a funny thing. Cool. So 0, 0. Huh. It's an interesting thing to play with. It's a really interesting thing to play with. It's creating different types of correlations. I wonder why. I wonder how this is useful. And probably if we take a look later on at some concrete algorithm examples, then we can understand how those things are being used. Yeah, I don't think that's correct. Again, because it's everything 0. It's a bit sad that I hope they fix that. If it's really a problem, because that's such a beautiful tool to gain intuition. Because if I send that to run the simulator, it should just be 0, 0, 0, 0. Then it should be, because that's basically what I would expect, because none of the Z's is activated. Cool. So for the moment, I'm gonna keep my. Sorry, I messed up with this. Oh, I broke it. Let me delete it. So for the moment, we're gonna keep it this way. I'm gonna stay at that point with the experiments with the control Z. It seems it's a different type of correlation. Yeah, obviously 0, 0, 0, as I said. Okay, so yeah, so that kind of that was an interesting. Let me see. Yeah, it's a different type of correlation. Interesting. That's pretty cool. It can be a bit overwhelming to play with this stuff, though. Yeah, whatever. To sum it all up, Control X can help it create a different a type of correlation where they all always agree. A Control Z, it helps you create a type of correlation where they disagree in equal probabilities. They agree or disagree, always in equal probabilities, but you always know in which way they're going to agree and in which way they're going to disagree, which this can be definitely helpful. And cool.